To motivate the concept of convolution, consider the following example. Suppose we are given, let's say, the stock prices up to some moment t, let's say up to the moment t equal 1. So t equal 1 is the current time, and we are looking at the historic prices. And we are trying to figure out overall trend. Typical stock prices fluctuate a lot, and those fluctuations make it harder to see the trend. So one of the first things that researchers usually do, they try to smooth the data. That is, at every time moment, they look at the preceding historic prices and take a weighted average of those prices. Now, people can use different weights, but it's natural to think that the further you go to the past, the less relevant those data are, so the weights should be smaller. A popular method is to assign smaller weights to older data. A typical weight function is on the picture. The further you go to the past, the smaller the weights, and very old data has almost zero weight. One example of such function, we start from the decaying exponential function e to minus t. And so we, since we go into the past, we replace t in the exponent with t minus tau, where t is today's date, tau is the past time moment, and t minus tau is how much time elapsed since that past moment until today. So the larger t minus tau, the smaller should be the weight. So we replace t in the exponent with t minus tau. Okay, so our expression for the weighted average of the historic prices will be, so at every past time moment tau, we take the price at that moment and we multiply by the corresponding weight h of t minus tau, for example, e raised to minus t minus tau, okay? And we add this up. So we take the integral from the very beginning until the current moment. And this integral is called convolution. Now, let's record the value, let's plot the value of this integral as a new data point. So the y value of that point would be the value of this convolution integral. And by the way, the notation for such convolution integral is people usually write h weight function, in our case e to minus t, then star, then f, the function that represents prices. So h star f, that's convolution of h and f. And all this applied to the current moment t. Finally, so we are going to do this averaging every day. So every day we look at the preceding historic prices and we do the weighted average. And we are getting a new time series. And that time series fluctuates less, and usually it retains the original trend that researchers were looking for, and such new series is easier to analyze. So that series is called convolution function. So this is a result of convolution of two functions: the original time series that stores stock prices, and the weight function. Here's another example. Suppose we have first order linear differential equation. The left side is y prime plus y, and we have the initial condition at 0. We know how to solve such equation. First, we look at the integrating factor. The integrating factor is e to the t. You multiply the left and the right side by e to the t. Then the left side becomes derivative of the product of e to the t and y. And the right side is just f times e to the t. Now we integrate both sides. E to the ty will be integral of the right side. Now, inside of the integral, just so that we wouldn't confuse the variable of integration and t outside, let's denote the variable by tau. So this integral, this antiderivative is defined up to a constant c. And since we have the initial condition y of 0 equal 5, we can rewrite this expression as a definite integral. So c equal to 5. And then we have a definite integral from 0 to the current moment t of e to the tau f of tau. So indeed, this expression is an antiderivative of e to the tau of e to the t f of t, and when t equals 0, the left side will be y of 0, which is 5, and the right side will be 5 plus integral from 0 to 0, so 5 plus 0. So our initial condition is satisfied. Now observe that the exponential function in the integral can be written as e raised to minus t minus tau. So this integral is actually the convolution integral discussed in the previous slide. So now the answer can be written as 5e to minus t plus convolution of the function e to minus t and f. Such convolution describes this integral. One other remark. The term 5e to minus t, it's simply the solution of the homogeneous equation y prime plus y equals 0 with initial condition 5. And the convolution term, that's a solution of non-homogeneous equation with the 0 initial condition. A 0 initial condition because this integral, when t equals 0, this integral will return 0. You can look at it the other way around. The convolution function described in the previous slide, where we were talking about the weighted average, like moving weighted average. So that convolution function is actually can be described in terms of a differential equation. Okay, so this convolution function equivalently can be described in terms of the differential equation that it satisfies. What happens if we apply Laplace transform to a convolution of two functions? A remarkable fact is that we obtain a product, like ordinary product of two Laplace transforms. This makes Laplace transform very appealing when dealing with convolutions. The convolution looks like a fairly convoluted integral, but once you apply Laplace transform, it looks very natural. Here's an idea of the proof. So let's write the Laplace transform of the convolution function. So we have the Laplace transform integral. Now the convolution function inside, that's given by the convolution integral. Now you see, the integral with respect to t we have integral with respect to t and integral with respect to tau. So for each fixed value of t, we compute the integral with respect to tau. So on the picture, like for each fixed t, we look at all values of tau between 0 and tau equal t. So essentially, while computing this complicated integral, we are visiting every pair of t tau values enclosed in this sector. And essentially for every pair t tau, we compute e to minus st times h of t minus tau times f of tau, and we add them up. Now, we don't have to scan the sector the way we did, like first vertically and then add this up. We can also scan in a different direction. For example, we can scan horizontally first, and then add up the results. So we arrive to the following integral. So t runs from 0, so tau runs from 0 to infinity, and for each fixed tau, we look at t values starting from t equal tau to infinity. And for each pair t tau, we compute the product of our functions, and then we add this up. Now observe that f of tau is actually doesn't contain t, so you can pull it outside of the integral with t. So it belongs to the integral with tau. Now let's change the variables. Let's denote t minus tau by x. So t will be x plus tau. Okay, so t runs from tau to infinity. So x, which is t minus tau, will run from 0 to infinity. Now, instead of t, we are going to write x plus tau. And dx, since when tau is fixed, dx is the same as dt. So we have a new integral. Finally, observe that we can split this exponential term. We can write it as a product of two exponential functions. One depends on x, another on tau. And finally, observe that so after we split the exponential term, we move the part with tau to one integral, and the part with x we keep in the other integral. So now we see that we have product of two integrals, and each integral represents Laplace transform. The first integral represents Laplace transform of f, the other integral represents Laplace transform of h. So we have product of two Laplace transforms. That's the proof. A convolution with the delta function is particularly interesting. To motivate this, let's start with discrete delta functions. So what is a discrete delta function? So discrete delta function is one which its domain is just integers, and at t equals 0, it returns the value 1. At all other t values, it returns the value 0. Similarly, a shifted delta function concentrated at t equals 5. That's a function that at t equals 5 returns 1, and at all other t values it returns 0. Now, a linear combination of two delta functions, for instance, delta function concentrated at 3 minus 2 multiplied by delta function concentrated at 5. So that's a delta function. That's a function which is 0 everywhere except t equals 3 and t equals 5. At t equals 3, it returns the value of 1 because that's what the first term returns. And at t equals 5, it returns the value minus 2. Similarly, you can decompose any discrete signal as a linear combination of delta functions, where so each delta function will be multiplied by the corresponding y value of our discrete signal. So we can write this in the compact form. So we have summation. So each term will be a delta function focused, concentrated at some t value, let's denote it by tau, multiplied by the y value of our signal at the t value tau. So this looks very much like convolution discussed in the previous slide. In the continuous case, the formulas are similar except that we replace summation with integration. So f of t is, so we have summation of f of tau times a shifted standard delta function. Okay, so we have this convolution integral. In other words, we have a convolution of f and delta function at time t. For example, let's consider the let's recall that when we have impulse at the right side of the ordinary differential equation, the best way to solve such equation is to use Laplace transform. Let's recall how to do that. So when we apply the Laplace transform to the derivative of y prime, we'll get s times Laplace transform of y minus the initial condition, minus 0. Now the y term, its Laplace transform is just capital Y, and the Laplace transform of delta function is 1. So now the left side has common factor y. So if we pull it out, we have y times s plus 1. So we can isolate y. So y will be 1 divided by s plus 1. And the inverse Laplace transform of this is just the exponential function e to minus t. That's for all t greater than 0. This doesn't apply to the moment t equals 0, like before the delta impulse. Here's another example. Suppose this time the same equation, but the right side is e to 2t. As usual, we apply the Laplace transform. The Laplace transform of e to 2t is 1 over s minus 2. And again, the left side is the common factor y of s times s plus 1. So when you isolate y of capital Y of s, you get a product of two fractions. Now, this time, our goal is not to compute the answer explicitly, but to relate to the convolution. So we have product of two Laplace transforms. So the original function will be the convolution of inverse Laplace transform of the first factor, which we just computed. And the Laplace inverse Laplace transform of 1 over s minus 2, which is e to 2t. That's the right side of our equation that we started from. So we see that the solution to our equation is a convolution of two things. The first term is the response to the delta function. And the second term is what our right side was at the beginning. Okay. So this is true in general. Whatever the right side you have, the solution will be the convolution of that right side with the response to the unit delta function. Now, how to compute this convolution? We go back to Laplace transform and we do partial fraction decomposition. Okay, so it will be just 1/3 of the difference between the fraction 1 over s minus 2 and the fraction 1 over s plus 1. Now, the inverse Laplace transform of each fraction we know. The inverse Laplace transform of the first fraction will be e to 2t, of the second will be e to minus t. So our final answer will be just difference of two exponential functions divided by 3. Note that e to 2t over 3, that's a particular solution, and e to minus t, that would be the solution of homogeneous differential equation. If we replaced the right side by 0, the solution of such homogeneous equation would be e to minus t times some constant. In our case, also 1/3. Suppose you have a time series. For instance, suppose you recorded stock prices at the discrete time moments, t equals 0, 1, 2, 3, 4, and so on. Now, suppose we want to analyze the trend. Note that the series shows some random spikes and rapid oscillations. For the purpose of analyzing the trend, they are often irrelevant, and practitioners often prefer to, as a first step, to smooth the time series. In other words, they want to produce a new time series which would retain the same trend, but where the data wouldn't change so rapidly. For example, at time t equal 1, we can take the average of the current price and the previous price. Then at time t equal 2, we can take the average of the current price P2 and the previously computed average. At the next step, at time t equals 3, again we take the average of the previously computed sum and the current price P3. So we are getting a new number. What's interesting is the expression in the parentheses that we get. You can write it in compact form as a summation from n equals 0 to n equals 3 of the terms which consist of Pn and the weight 1/2 raised to 3 minus n. The expression like this is called a convolution. Its distinct feature is that the index n appears either only by itself or in the expression like 3 minus n. So here 3 is represents the current time. So like current time minus n. One more remark. Observe that we have a recurrent relation between consecutive values of f. Such recurrent relation plays the role of a differential equation in the continuous model.